So now we're going to look at what happens after we've passed the equivalence point in our weak acid strong base titration curve. And I want to point out that overall the mathematics that we use to find this answer is almost exactly the same as we use to find the pH after the equivalence point in our strong acid strong base titration curve. So there's not that much difference between the two. So the fact that we're dealing with a strong acid or a weak acid really doesn't matter after the equivalence point. So if you go back and look, the basic steps of this calculation are the same that we did after the equivalence point of our strong acid strong base titration curve. So the first thing we want to do is prove that we're past the equivalence point. So same deal, I'm starting with a certain amount of our weak acid, acetic acid. I'm adding some base to that. I understand that there's going to be a neutralization reaction going on. So the first thing I want to do is find the number of moles of each species. For our acetic acid, molarity times volume. So I've given you the molarity. Volume is 50 milliliters. This tells us we have 5.0 times 10 to the minus third moles of our acetic acid initially. I then want to find the amount of hydroxide we've added. So mole is equal to molarity times volume. Molarity is 0.1 molar, that was given. The volume is 60 milliliters or 0.06 liters. So we get that we've added 6.0 times 10 to the minus third moles of our base. So what we always want to do when we're doing a neutralization titration like this is we want to compare the amount of acid that we're starting with to the amount of base that we've added and see the relative amount of moles. In this case, because of the number of moles of hydroxide are greater than the number of moles of weak acid that we have initially, we know that we are past the equivalence point. So with this, we need to change our thinking in terms of the calculation that we do. So remember, we always want to find out where are we at in terms of our equivalence point, because that tells us how we're going to do the calculations past this. So because we're past the equivalence point, the amount of weak acid is really not the important issue. What we want to do is find out how much hydroxide is remaining. So the pH of our solution is going to be determined by the concentration of hydroxide. So now what we're going to do is we're still going to understand that there is a neutralization reaction going on between the hydroxide and our weak acid, and they're going to react with each other in a 1-to-1 mole ratio. But what we're interested now in is how much hydroxide is left. So we're going to take the number of moles of hydroxide that we started with, so we found that right here, and then subtract off the number of moles of weak acid that we had initially. So we've calculated that right here. And when we do the subtraction, what we want to find out is how many moles of hydroxide are left over. So when we've done the subtraction, we realize that we have 1.0 times 10 to the minus third moles of hydroxide left. And so this is the idea. Here, it doesn't matter if we're dealing with a weak acid or a strong acid. In this step, it's just, how many moles of acid do we have? So these calculations are exactly the same as we did with the strong acid, strong base titration. So we want to find out the number of moles of hydroxide, so we just calculated that, and then we need the concentration of hydroxide. So we're back to looking at V total. You got to remember that the total volume is equal to the number of milliliters of weak acid we started with, plus the number of milliliters of base that we've added. So if you look at our original question, it said that we started with 50 milliliters of weak acetic acid, and then we added 60 milliliters of sodium hydroxide. So our V total, or the total volume of this solution, is 110 milliliters. So we use this to find the concentration of hydroxide. So here, notice we're not talking about equilibriums anymore. Our weak acid is completely been neutralized. So the idea of equilibrium is gone. We don't need Ka or Kb. What we want to find is the concentration of hydroxide that remains. So we know how many moles of hydroxide we have. We know what the total volume of the solution is. We divide one by the other and we get the concentration of hydroxide, and that's what's going to determine the pH. So once again, we need to get to information about pH. So the first thing I'm going to do is find the pOH, which is the negative log of the concentration of hydroxide. So we just calculated the concentration of hydroxide right here. I take the negative log of that number, I get that the pOH is 2. And then I realize that pH is equal to 14 minus pOH, or my pH is equal to 12 in this case.